Hi everybody. I'm just noticing that this review title has an error in it. This has to do, we're not doing, the cast rule was done in review number 6. So in this review, we are going to do problem solving. We're going to do sine law, cosine law, and we are going to do sine law ambiguous case. Oops, there we go. Just trying to, okay, so that's Castro we did in review number 5. Note that although this is called review number 6, it is really the second half of your unit number 5. Okay, so the reviews don't exactly correspond with your units, but by the time you do review number 8 and complete that, you will have reviewed all the material in the grade 11 course. Okay, so again, this is review number 6, which is a review of the second half of Unit 5. Let's review the conditions for sine law. Side, when you're given side, side, angle, 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 side, and angle, side, angle. So when you're given two sides, side, side, angle, or angle, angle, side, or angle, side, angle, you're using the sine law. The conditions for use of the cosine law are side, 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 and side, angle, side. Okay. The two forms of the sine law are just simply A over sine of angle A, and it's side of B over sine of B, and that equals length of side C over sine of C. The other form is just the reciprocal version, which is sine of A over A equals sine of B over B equals sine of C over C. Now, this one I prefer to use when I'm calculating a side because the side is on top. And I prefer to use this version of the sine law because when I need to find an angle because the sine of an angle is on top. Now, the two conditions for cosine law are as I explained before. And the cosine law for finding an angle is angle A equals the inverse cos of b squared plus c squared minus a squared all over 2bc. And the cosine law for finding a side is simply a squared equals b squared plus c squared minus 2bc cos of a. Alright, so let's do a few examples. Two ships left Port Hope on Lake Ontario at the same time. One traveled at 12 kilometers per hour on a bearing of 235 degrees. The other traveled at 15 kilometers per hour on a bearing of 105 degrees. How far apart were the ships after 4 hours to the nearest kilometer? So just to remind you, a bearing is a clockwise angle from the magnetic north. So all that means is if we were to draw a crude little compass here, I guess it's not really a compass, but we're just going to label these north, west, east, and south. So this 235 degrees is measured from the magnetic north, or this north here, and we're just going to count. This is 180, and 180, if we go up to here, that would be 270, so that's too far, so it's going to go just a little bit below that. This is just a sketch. Okay, so two ships, okay, one traveled on a bearing of 235 and the other traveled on a bearing of 105. So that's going to go 105. This is 90 and 105. It's going to go over there. So this is 105 degrees and this is 135 degrees. Okay, so this one went 135 degrees from the magnetic north. This one went 105 degrees. So I hope it doesn't, our labeling and so on and so forth doesn't get too messy. I'll just put that like that. Okay, so two ships left port on Lake Ontario at the same time. One traveled at 12 kilometers per hour. And let's see, we're looking at how far apart were the ships after 4 hours. So that means this ship on a bearing of 235 degrees traveled 48 kilometers because 4 times 12 is 48. And this other ship traveled at 15 kilometers per hour for 4 hours. So 4 times 16 is 60 km, and this is km. Alrighty, so they want us to find the distance between the two ships. So I'll just extend that a little bit just to maybe make my diagram a little bit clearer. Okay, so here. So I'm going to call this, I'll just label this B. Okay, and this one C and this one A. So opposite day, we want to find out how far apart were the ships after 4 hours. So I'm going to call this little a. This is my south. This is little a. This side I am calling this, I labeled this vertex A. So this is angle A. And I want to find the opposite side to angle A, so I called that little a. So I'm going to say let A be the distance between the two ships, and I guess we'll call them ship B and ship C, and let A, B, C be the labels for the angles as shown. Okay, so now we're in a position to find angle A. Angle A will just simply be 135 minus 105, and that will be, sorry, that should be 235. Yes, that's my mistake. So this is 235 degrees. Okay, so this is 235 and this is 105. I apologize about that. That's 235 degrees. So angle A is equal to 235 degrees minus 105 degrees, and that is equal to 130 degrees. Okay, so now this little angle A right there is 130. So notice we have side, angle, side, and that's the condition for the cosine law. So side is 48, this angle is 130, side 60, side angle, side, we can use the cosine law to find the distance between the two ships. So we will set it up into this. A squared equals B squared plus C squared minus 2A, minus 2BC minus 2BC cos of A. So let's plug it in. A squared equals, now B is 60 squared, and C, opposite to C, is 48 squared minus 2 times B, which is 60, 48 cos of angle A is 130 degrees. Okay, and so I'll calculate that, and that works out to be 9606.456632. Now they want it to the nearest kilometer. So A is approximately, take the square root, A is approximately 98. The two ships are about 98 km apart. Okay? Alright, that was an example of a two-dimensional problem. Notice we're basically working with one triangle. Let's look at a three-dimensional problem. So there's usually more than one step. And usually in a three-dimensional problem, you have to work with two or three 2D triangles. So that's all it is, really. Okay? The difficult part in three-dimensional problems is interpreting the question. Okay? How do we interpret it and draw our diagram and try to make sense out of it? Well, let's take a look. Let's do this as best as we can. To determine the height of a pole across the road, so let's just draw our road, and there's a pole here. Okay. Justin takes two measurements. He stands at point A directly across. Now for the purposes of my diagram, I'm not going to draw it directly across because we're going to lose the third dimension, right, since we're in a two-dimensional plane. So I'm just going to draw it here. So imagine A being a directly across from the base of the pole, and determines that the angle of elevation to the top of the pole. Well, let's try to draw a triangle here. We'll just do that as best as we can. I'm wondering if I should have drawn this pole just a little bit further. Well, we'll just work with it. Things will never be perfect here, so here, that's at right angles, if you can imagine. So here's our pole, and I'll call that base of the pole, I'll call the base of the pole B, and he's at point A, and that angle of elevation is, they told us it's 15.3 degrees. 15.3 degrees. Okay? He then walks 30 meters parallel to the freeway, or I guess to the road. So he's walking this way to point C, and that is 30 meters parallel to the freeway to point C, where he sees that the base of the pole and point A are 57.5 degrees apart. So let's draw that. And this is going to be 57.5 degrees apart. So from point C, they're saying that this is 57.5 degrees apart. Now, even though maybe we don't see it in the drawing because I couldn't draw it here, we would lose a three-dimensional drawing in a two-dimensional space. But just know that this is in point A is intended to be directly across from the base of the pole, and he walks this way to point C. So this angle here is a right angle. That angle there is a right angle. Okay? Let me draw that a little bit better just to help us out. Okay, that's the line of sight angle of elevation to the top of the pole, and this is up. Okay, and this is the base of the pole. Alright, so I think we have all the information we need. Notice we have two triangles, one here, um, and we should have all the information. Now find the height of the pole. So the variables, let's just do our statement here. We'll call this H. Calculate the height of the pole to the nearest meter. Let H be the height of the pole to the nearest meter. Okay, there we have it. Okay, I think we're ready to start. Well, we have, let's just look at this. There's the height of our pole, and we have this angle of elevation. All we really need is this side. So this side is opposite angle C. Okay, we'll just uh, let the let the variables A, B, C be as shown in the diagram. So always remember that problem solving requires let statements, okay, and conclusions. So we'll call this little c. We're going to find little c because it's opposite angle c, right? So the side opposite the angle is denoted with the lowercase. Alright? Alright, so we're going to find side C, and notice we're solving this two-dimensional triangle. We're going to find this side, then we'll solve this two-dimensional triangle, and these two triangles together make a three-dimensional problem. So we're just working, we just do a step at a time, a two-dimensional, we work with that, and then we use that information to find the uh, or what we're looking for on another two-dimensional triangle. Okay, so we know we'll use tan, opposite over adjacent, to find C. Tan of 57.5 degrees equals C over 30. So C equals 30 tan 57.5 degrees, and that is approximately equal to 47.0956731. Okay, now we know C. Now we can find the height. I'm going to continue my work up here. So this is in triangle ABC. This is, we're looking at triangle ABC for this calculation, and for this calculation, why don't I call that triangle ABD? Triangle ABD to find the height. I could have called that little a, but I called it H for height. Okay, so now we have tan of 15.3 degrees equals H over opposite, right? H over adjacent for tan. So it's 47.0956731. I like to maintain a high degree of accuracy. Um, so H, that's why I keep all those decimal places, is equal to 47.0956731 times tan 15.3 degrees, and that is approximately, they just wanted it to the nearest meter, 13 meters. So the height of the pole, the height of the pole is about 13 meters high. Okay, so again, make sure, you know, you do a lot of practice. You have other review sheets with which you can practice. Let's just look now at sine law ambiguous case. There are 6 scenarios that we looked at. There's 4 scenarios when angle A, or the given angle, is less than 90 degrees. And then there's 2 scenarios when angle A is greater or equal to 90 degrees. So let's take a look at that. Now, what I want to illustrate to you, people wonder what this B sine A is all about, and I'm just going to remind you to help you wonder why we're calculating B sine A. If you are given information, now the sine law ambiguous case only comes up when you are given angle side side, okay? Any other scenario you're fine with, but when you're given angle side side, then there's this possibility of the ambiguous case. So if you're given an angle A, and usually you're given side A and side B. Now if you're only given this angle, right, you're given this angle, you're given the opposite side, and you're given B. Do you see that? Well, we don't know what this angle is. This A could be swinging there or there or there. We just don't know where it ends up because we're not given that information. Also, we don't know is the angle size of side B of angle B. So we're just given this, and we're not really sure how to place these things, and that's why it's ambiguous. This is solid, this angle is solid, but we don't know the length of this, right? This is solid, we know the length, we know the angle, and this length we know, but we're not sure how it relates to the height of the triangle, which is this. Okay, so notice sine of A equals h over b. So the height of the triangle equals b sine A. So can you see that this is the height of the triangle? Okay. So what is this saying? Well, let's take a look at this. This is A, this is B, this is angle A. So I always recommend when you're doing sine law ambiguous case to always place your angle there, the opposite side B, any given angle, write it there, the opposite side A, and then side B. Okay? So notice if A is less than the height, no triangle is possible. So if A is less than height is less than B, no triangle possible. Therefore, no solution. Okay? Now, if A equals the length of the height, then the only possible triangle you can have is this. Right? If the given side opposite the given angle equals the height, then this is the only possible scenario where A equals height. So in that case, we have a right angle triangle. We have one triangle, one solution. Now this is probably the easiest case. If you know that A is larger than B, then there's only one scenario possible. If you know A is larger than B, you only have one triangle. Now, if A is between the height of the triangle, remember B sine A is the height, is less than B, then you have two possible triangles. Here's your A. This is B. Now, there's our height. So we don't know where to place A. If A is less than B, but it's also greater than the height, A could be there or A could be there. So you have height is less than A is less than B. So there are two possible triangles. This one, we'll call that B1, or this one, B2, right? Because if you put A there, okay, there's one triangle, but because we don't know this angle, we don't know where to put this side A, it could also end up there. So here you have two triangles, two solutions. Okay? Now what happens when A is greater than, angle A is greater than 90 degrees? And side A, so here's A, this is B, but side A is less than B, so it could be there or there. Notice that there's zero triangles, zero solutions, right? Because if you don't have a triangle, there's zero solutions. Now if A is greater than B, then it's easy. This is B. Notice A is greater than B, so this is one triangle. When you have one triangle, you can only have one solution. So let's try two problem-solving questions. All right. In this situation, draw a sketch of each scenario. Calculate, let's see, I think there's a little few typos here. Label all side lengths to the nearest tenth of the centimeter and all angles to the nearest degree. Okay, let's just, okay. What we want to do is we're going to solve this triangle. We're given side, side, angle, and we need to solve it. Okay, so let's first of all look at this. When we're given side, side, angle, we want to determine how many solutions there are. So let's just take a look. So let's draw what we have here. We're going to, the given angle is angle B, so always put the given angle there, regardless of whether it's called X, Y, Z. You put the given angle there. B is 3, and what we're going to do, what we want to see is how many solutions are possible. So I'm going to just calculate the height, which is, in this case, they're telling us C is 5.5. Sorry, B is 3. I got this a little bit wrong here. Right? So C is 3, and I'm not sure where that's going to end up. Sorry, B is 3, and C, let's see where it ends up. C is 5.5. So the other given side goes here. B is 3, so opposite vertice B, we put the 3. Let's calculate the height. So the height in this case is, well, we can go sine of 30 degrees equals h over 5.5, and h is equal to 5.5 sine 30 degrees, and that is equal to 2.75. Okay, so notice height is less than, B is less than C. So in other words, 2.75 is less than 3 is less than 5.5. Agreed? So notice since the 3, the side opposite B is right in between the height and the other given side, we have two cases here. Two cases are involved. Okay, so one possibility is here and one possibility is here. Why don't we call this, we'll just draw the two cases separately. so that we don't have any confusion. Let's just divide this up into two cases. We'll do case 1. Do you see how we have two triangles possible? Two triangles, therefore two solutions. Okay, let's do case number 1. Case number 1, we'll do this one here. Call this A, B, C. Here's our 3. Here's our 5.5. Okay, so sine of C over 5.5 is equal to sine of 30 degrees over 3. So solving this, angle C is approximately 66.44354 degrees. Okay, that makes angle A. Well, why don't we find the other angle C for case 2 first? So you can, just to emphasize. So the other case will be this one. I'll call that one C as well. Well, we can't call it the same thing in this diagram, but here I'm drawing two separate diagrams. So here is case 2. It's going to look more like that. So this is B, A. So here angle C is equal to 180 degrees minus 66.44354 degrees, which is approximately equal to 113.55646 degrees. Okay, so angle A is equal to 180 minus, now let's see, angle B was 30 degrees, minus 30 minus 66.44354, which is 83.55646. So now we're in the position to find little a over sine of 83.55646 equals 3 over sine 30. When you calculate that, A is approximately equal to 5.96. So just doing a summary of everything we've calculated. Angle C, they want it to the nearest degree, and angles to the nearest degree and lengths to the nearest tenth. So angle C is approximately equal to 66 degrees. Angle A is approximately equal to 84 degrees. And little a is approximately equal, they want it to one decimal place, 6.0 centimeters. Okay, let's finish off this guy. Angle A equals 180 minus angle B, which is 30 degrees. Now this is our 3, this is our 5.5. 180 minus 30 minus 113.55646 degrees, which is about 36.44354 degrees. And now we can calculate side A, which is this guy, right? Side A corresponds to that. Is A over sine of 36.44354 is equal to 3 over sine of 30. A is approximately 3.56418. So now we have A is approximately 3.6 centimeters. Angle C is approximately 114 degrees, and angle A is approximately 36 degrees. Okay, so that's kind of a lot of work First you test, see how many cases there are. There's 2 cases, so then you know your triangle can either look like this, and then, or your triangle can look like this. The trick is know how to calculate the second C, because we don't know this is why it's ambiguous, because you have the 2 cases. Let's look at this next example. Let's see, the given angle is angle C, and that's 33 degrees. So opposite the C is 5.2. I'm just going to draw it like that because it's less than A. So let's just calculate the height and see if this even forms a triangle. Because if side C is less than the height, we don't even get a triangle. So let's just try it. Sine of 33 degrees is equal to sine of 33 degrees is equal to h over 11.1. H is equal to 11.1 sine of 33 degrees. So I just have to get a calculator. There we go. So pulling out my calculator, 11 sine of 33 degrees, and I'm in degree mode, always check that. I get, let's see, I get approximately 6. Okay, I'm just going to check that. Sine of 33, close bracket, equals that, times 11.1 equals, it's about 6.0. Okay, so since the opposite side, this is C, and this is little b, right? Since C is less than the height, no triangle is possible. Okay, let's do an example with 2 forest fires. P and Q are 20 kilometers apart. A ranger at station Q sees a fire 15 kilometers away. If the angle between the line PQ and the line from P to the fire is 25 degrees, how far to the nearest tenth of a kilometer is the station? Oh, this is another long solution because I'm anticipating some ambiguity here. Let's just do a test, okay? P, 2 fire stations, P and Q, are 20 kilometers apart. A ranger at station Q sees a fire 15 kilometers away. So let's call this fire 15 kilometers away. If the angle between line PQ and the line from P to the fire is 25 degrees, how far to the nearest tenth is P? We need to find this, Q. Let's do our test, okay? This is little q. Okay, we better do our test. So H sine of 25 degrees is equal to H over 20. H equals 20 sine of 25. H is approximately equal to 8.5. Uh-oh. Notice that H is less than little p is less than little f, right? So this side is between the height and that side. That means we have 2 possible triangles and 2 solutions. Ambiguous case, even though it's a real life application. So we'll just say let Q be the distance between, I'll draw the two triangles in question. Let's just do this. I'll draw it over here. We'll divide it in half. Hopefully we'll have enough room. So here's case number 1. Okay, so this is 20, this is 15, and this is point P. There's our fire, 25 degrees. Case 2 will look like this one. This is P, this is Q, this is F, this is case number 2. And this is 25 degrees, 15 degrees, and no, a length of 15 kilometers, sorry. And this is 20 km. And this is km, this is km. So let's get started. This is Q, right? Alright. So, sine of F over 20 equals sine of 25 over 15. So, if you could, when you do the calculations, angle F is approximately 34.29757. Angle Q is approximately, well, it's going to be 180 minus 25 minus 34.29757. That's approximately 120.7024,298. And now we can find little q over sine of 120.7024,298, and that equals 15 over sine of 25. And in this case, q is approximately, they want it to the nearest tenth, so it's 30.5. Notice I round my final answer only. Let's do this one. In this case, in the second scenario, angle F is equal to 180 minus 34.29757, and that is approximately 145.70243. Angle Q is approximately 180 minus 25 minus 145.70243, which is about 9.29757 degrees. So Q over sine of Q is equal to 15 over sine of 25. So Q is approximately, oh, why don't I put the value in there? Sine of 9.29757. So Q is approximately 5.7. Let's write our conclusion. I've run out of space. The distance to the fire is either 30.5 km or 57 km. And that should be, 5.7 km. Okay? Ambiguous case, two possible solutions, right? Ambiguous case, we've tested it. So always remember, whenever you're given angle side side, right? Angle side side, angle side side. right? This was all angle side side. There's the potential for an ambiguous case, which you have to test for. We tested, we found that the side opposite the given angle was between the height and the other given side. So there are two solutions. There's two triangles possible with two solutions. So that's what happened. In this case, two possible distances to the fire, and you have to show both. Okay? Good luck studying. If you have any questions, you can ask me during tutorial time or during class time. And remember, practice, practice, practice.